Okay, and now this question, which up here turns out to be an interesting mathematical problem. If I give you a simple graph, which is not special, is it then possible to make it special by adding multiple edges? So this graph was not special, remember, because this vertex and this vertex have the same degrees, but can we add multiple edges such that it becomes special? And when I say adding multiple edges, you're not allowed to add an edge here, for example. You're only allowed to add extra edges if you want to. This can be done for that graph, for example, like this. So you add there are 5 edges here, 2 edges here, and then if you compute the degrees, it looks like this, and it's very nice, and no neighboring vertices have the same degree. For the graph down here, which was also not special, you can do it like this. And that also works, and the degrees are like this. But of course, doing this is, at some point, it becomes a tedious exercise to draw all these edges all the time. Especially if you want to draw like 20 or something. So we can also just encode this doubling edges thing by using weights on the edges. So, for example, we could put a 1 on this edge because it's just a normal edge. We could put a 5 here because there are actually 5 edges here. And that counts as 5 towards the degrees, for example, with this vertex. Then we get a number of 1 here, 1 there, and 2 there, because you have a double edge here. And you can also put these numbers in here. So this whole game of doubling the edges is actually just a matter of adding weights or numbers to the edges. And then the question is, can you make any simple graph special by weighting the edges and then look at the weighted degrees? And that's a fairly easy question, because no, you cannot always do that, because of this silly graph here, which is just 2 vertices and 1 edge between them. Then no matter what you put here, these 2 guys will always have the same weight, of course. But it turns out that this silly graph is the only case where it goes wrong. It can actually be done for any other simple graph, and moreover, you only need to use weights 1, 2, 3, 4, and 5. You don't need to use weights which are greater than 5. So this is a result from 2010, and that was proved by a very clever algorithm that finds these appropriate weights. But what about if you're more ambitious and say, well, okay, now at least I know it can be done, and you can do it with also only 1, 2, 3, 4, 5. But then the talk was called the 1, 2, 3 conjecture. So the ambitious conjecture, the open problem is, can you do it if you only allow 1, 2, and 3? That conjecture is back from 2004 and still open, and the result I showed you before, that if you also allow 4 and 5, then it's possible. That result is the best possible so far. So you don't know about 1, 2, 3, and 4. So this is the very interesting open problem, which is the main focus of my PhD research. And then why do I ask about 1, 2, and 3? Why am I not more ambitious and ask about only 1 and 2? And that is because that turns out to be very false. There are many graphs where you cannot do it. Here are 3 examples. You cannot make these special by only using weights 1 and 2. And it actually turns out that this problem, checking a graph and deciding whether you can do it with 1 or 2, that problem turns out to be NP complete. So all these edge weighting problems, where you try to make graphs special, they're also very interesting from an algorithmic point of view. And then my time is up. So.